Hamsters welcome you, friends. Today will be devoted to the creation of an ultrasonic cleaning bath, which is based on a 60 watts Langevin piezoceramic emitter. We will look at what the device consists of, how to configure it, and we will learn how to clean things no worse than Mr. Proper. So make yourself comfortable, we begin. Before starting to dissolve our fingers in an ultrasonic bath, let's look at how mechanical vibrations arise on simpler systems. One of the examples of oscillatory mechanism is magnetostructures, which can be compressed or stretched under the influence of a magnetic field. These parameters are possessed by ordinary ferrite from the old grandfather's receiver. To start the experiment, we need a signal generator, a pulse density modulator for adjusting power, a half bridge, an adjustable power supply and oscilloscope for visual evaluation of the signal. Next, on a small mandrel, we wind a coil of thick copper. In my case, there is about 50 turns of wire, 2 mm. On a pulse modulator, we set the power at 100%. By turning the knob on the generator, we find the resonance of the system, which in a particular case look like two vertices that we need to align. The frequency of a particular rod is 8.5 kHz. Approaching mechanical resonance, it is seen how a drop at the top of a ferrite rod begins to vibrate, changing its original shape. At some point, the amplitude of the vibration reaches such a value that the water breaks into thousands of small particles. The size of such drop depends on the mechanical system. The higher the frequency, the smaller the drop. Such a magnetostrictive system is not perfect, because at the certain power threshold brittle ferrite is turned into pieces. As it has happened now, 15 watts was too much. Maximum mechanical stress occurs in the middle of the rod. The result is an explosion. As an experiment, we connect the most ordinary piezoceramic emitter to the generator. As it can be seen, formed droplets are slightly larger than in the previously presented version, since now the resonant frequency is 2 times lower here and corresponds to 306 kHz. Now we turn to the Langevin radiator, named after the French physicist who was involved in magnetism. The electromechanical frequency of this gland is 40 kHz. The evaporation of water on it is more like an eruption of a volcano. In the next experiment, we will try to obtain ultrasonic levitation. Make small objects fly in the air. At a resonance in Langevin, a standing ultrasonic wave is generated. In this case, the particles of matter at the end of the patch oscillate in the vertical direction with an amplitude of tens of microns. These vibrations are easily transmitted to the air. If a reflecting surface is installed at a certain distance from the emitter, then the radiated and reflected waves will add up, forming standing sound waves in the air. To make the ball with polystyrene foam levitate, it must be placed exactly in the acoustical pressure unit. If you turn off the system, the entire house of cards will collapse. We understood the principle of work. Now you can take a closer look at the emitter. On the front side you can see the sandblasted mud surface, which provides better adhesion to glue and tank. The volume of such a vessel is 1.5 liters. The material is stainless steel. We center the emitter at the bottom of the vessel and clean the place where it will be located. Ideally, this place is best treated with sandblasting, but I don't have it in my household. When the surfaces are prepared, degrease them with the acetone and dilute the epoxy glue. We applied with a thin layer on the walls of the tank and carry out the same procedure with the emitter. when W Langevin tries to crawl somewhere. So that it does not run away, it needs to be rubbed a little and then pressed down so that all the excess glue crawls out. After polymerization, the epoxide will acquire the so-called metallic hardness. Now is the time to make the case. We note the pre-measured dimensions on a 10 mm chipboard and start working. It is advisable to do such an operation at night, when all the neighbors are sleeping. In the end, there will be 5 even pieces. All that is needed is to secure the plywood walls more reliably so that nothing falls apart. Ideally, the box should come out slightly smaller than the dimensions of the gastronome container. To control the operation time of the buff, you need a timer. A suitable circuit we found on the internet. But the circuit board itself had to be bred, as it simply was not in the description. The result is a small board with a fairly decent size. We power the system and see how something lit up. A short press on the encoder button turns the timer on and off. Turning the knob allows you to select the time in minutes from 1 to 99. After the specified interval has elapsed, music plays, and then a siren sounds, which can be turned off by pressing the encoder. Now it's up to the generator, the heart of the device. We place the elements as densely as possible, so that there are no high-frequency interference. The generator itself is called a push-pull. The IRFZ44 transistors work best. They are applicable. Management comes from the driver chip IR2153. Since the frequency control will be manual, in some modes the transistors will be very hot. It is advisable to use a radiator with a thick base, since its heat dissipation will be much more efficient than that of a piece of aluminum lacquered on the left, which overheats as a schoolboy on a first date. The temperature will be displayed on a Chinese thermometer. It costs about $2. All the energy of the buff will be pumped by a pulse transformer from a computer power supply. The size of the transformer does not matter. 60 watts for them as a dummy for a baby. We will evaluate the consumption of the entire circuit according to the readings of an emitter connected in parallel. The power supply for our task needs to be rather big. This charging board was taken from some kind of laptop. If the characteristics are correct, then it gives out 65 watts at a voltage of 20 volts. Now this bunch of parts need to be staggered. To do this on wooden boards, we know the previously planned places where the controls will be inserted. The clean works has ended. It's time to fill it up with sawdust. The rough marks are removed with a special drill. Since the nozzle is round, it remains to align the corners, and here the file comes into play. But you need to work with it carefully, since there could be chips on the decorative. On the reverse side there is a timer board, and on the front there is a thermometer that shows the temperature in tenths of a degree. We also install the rest of the circuit breakers and switches. We place the power supply inside. It is located near the blowhole for better cooling. We place the generator board opposite the fan. How does this walled pile of iron work? Let's figure it out. To start tuning, we set a voltage of 14 volts on an adjustable power supply. We check the stabilized voltage to power the driver chip. It should be 12 volts. Using the oscilloscope probe, we clean to the transistor's gate and check if a signal is present in the form of a emitter. If everything is in its place, we change the frequency with a variable resistor and make sure that the signal does not twitch and is even in the entire adjustment limit. Put the knob on the 10 and connect to the middle leg of the transistor. At idle, you can see how at the time of switching on a high voltage surge occurs, followed by a free damped oscillation. At the moment when the key is turned off, we see another peak. Ideally, this place should have a clean emitter. Let's try to connect the load in each lamp. We see how the attenuation disappeared. The leading edge of the emitter failed, and inductive emissions reach 700 volts. Part of this horror occurs in the board. Even a finger affects it. The same signal will be at the output of the transformer. One can see how between the inclusions of each shoulder a dead time of 1.2 milliseconds occurs. Beside the waveform, the work goes smoothly. High-frequency ringing can be put down by the snubber. This is the name of the chain of resistor and capacitor. Since it's very hot, the resistor should be powerful, about 5 watts. Connecting the chain to one of the shoulders of the push-pull, one can see how the waves are extinguished, though with a slight disturbance at the time of inclusion. This is the best thing I could achieve experimentally by selecting the capacity and resistance of the snubber for the circuit. With this sorted out, we move on. Since the emitter is a capacitive law, it is necessary to calculate a resonant inductor, which will increase the efficiency of work. The frequency of this Langevin is 40 kHz. We go into the electroid program and enter these parameters there. An ingenious program for doubles. You do not need to count anything, just enter numbers. According to the results of the calculation, the inductance has reached 3.2 millihenry. We will wind the transformer with a double wire to reduce the total resistance. The first version of the inductor was wound on the core of an unassembled transformer. I was upset. You can wrap a sample in one wire on a regular piece of ferrite. There will be heavy toll, but it will be enough for tuning. So, what are we seeing here? At one end of the emitter, there is a current transformer. In the future, it will be of little use. On the hot end of the inductor, we hook up a neon bulb for a visual assessment of the voltage. Pour some water into the gastronome containers. Connect the oscilloscope probe to the high voltage output of the transformer. We increase the voltage and see? Yes, we do not see it done. At resonance, at maximum consumption, the emitter sits down like a grandfather. I suspect that it is so because the inductor affects the low voltage part. We connect the probe to the hot end, adjust the frequency, and see how the voltage amplitude waves out of the scope of the oscilloscope. A span is about 1000 volts. The current at resonance is growing as it should be. If the water in the bath hangs, then the system becomes unstable. Here is a scheme of the electronic part. I try to indicate everything that is possible. As it can be seen, there is a contactor on the resonant inductor. There are two pictures with signals. The first work with capacitive load, and the second with resonance. Archived with all necessary materials for assembling, the bath is here. We figured out this part. Nothing burned out. So we move on. We connect all the connectors with power, control, variable resistor, cooler, and other things. Since the temperature sensor of the thermometer has a very convenient form for mounting, I did not come up with anything better than sticking it onto a piece of foil tape. We turn the encoding knob to start the bath for a predetermined time interval. The small left variable resistor causes the resonance frequency. In my case, the scale is equal to 3 amperes. The large right resistor provides more precise frequency control. Nearby is a resonant inductor choke. It is time for bath. Pour water till about 1/4 of the total volume. We adjust the frequency until there are funny cavitation bubbles, popularly called cobwebs, begin to form. Let's try to put there a piece of foil. This method is used to objectively evaluate the force of cavitation formed in ultrasonic environment. It destroys the oxidation coating on the surface of the foil. We add the remaining water to the gastronome containers, and we get exactly a liter of it. We turn the knob and find the resonance. it can be seen that the cavitation areas are not uniformly distributed. The life of small bubbles is complex and amazing. They oscillate, grow, reach a critical size, and boom! When a bubble collapses, a converging shock wave forms inside it. As a result, local sections with very high pressure and temperatures, up to the 10,000 degrees, are formed in the liquid. It is because of such cavitation bubbles even ordinary water becomes chemically active. Here is such a destructive force lurking around us. Let's get back to resonance. With a small amount of water, the maximum that happens is the Chladni figures, which depend on the frequency. A piece of foil perfectly demonstrates the effect of vibrational sliding along the bottom of the bath. It's time to add some magic powder to get Chladni figures, which are named after the German physicist Ernst Chladni, who discovered this effect. We figured out the principle of work. Now we can move on to the next part. The hamsters were given the task to find all kinds of junk. The task was perfectly accomplished. Let's see what happens with rusty glands. We found some interesting things, like a buckle from the times of ancient Russia and a huge bolt. We looked to ordinary table vinegar for help. As you know, it perfectly copes with any traces of rust. Pour a small amount of it so that the level rises above the parts by about a centimeter. We put a piece of iron at the bottom, wait a couple of minutes, then we launch a miracle machine. We do the same with the rusty budge. I was also glad to see the buckle. For the first time in many centuries it's tied. Now about the results. This is how glands looked before cleaning, and here is how they looked after. All inscriptions became readable on the budge. We were surprised by the old name. All the results of many years of the metal destruction became visible on it. The buckle has surprisingly little distraction. Apparently the blacksmith knew his stuff. The nut began to unscrew effortlessly, though there were still traces of rust under it. These two coins were found last year in the same pit. The degree of contamination can be considered as the same. We fill the bathtub with water and see what happens. We will clean this coin with a regular hard toothbrush. As you can see, a large coin threw off a little of its patina, but on the other, there still was dirt in the lower part. Here is another example. And coins before cleaning. Here is how they look like after cleaning. I'm wondering if coin restorers use this method. Let's see what's happened to the cartridge from the label refill, which was used by the French during the First World War. Unlike coins, the cartridge rested in some kind of mineralized soil, and no cleaning will save it. While my tea is brewing, let's see how ultrasound handles different things. We will conduct another experiment. These are two copper solid of Jan Casimir from the Middle Ages. We omit one instance in the gastronome container and try to clean the other in disodium salt, the second name of which is Chilon B. Since a party is already started, let's take a whole handful of coins and put them to the first solid, which is already taken, healing bath. It will remove all the dirt from the coins, and visually it will be clearly seen how Chilon B works. Take a teaspoon of this wonderful powder and dilute it in a glass of water. Throw a handful of previously cleaned coins, on which there are still oxides, dirt and so on. After a couple of minutes, you can observe how the reaction started at the bottom and the solution began to turn green. In general, it will be more correct to set all the coins on the edge, so the reaction will be more smooth. The next morning, the solution was annihilated and turned blue. We moved the sample in a tube with ordinary water. Chilon B converted all the oxides into a brown swamp. Now the coin will expose its body in the race of cavitation. As a result, we got a metal on which there is neither dirt, nor salts, nor patina itself. Coin is dead. Here is an example before cleaning, after cleaning in water and after cleaning in Trilon. Sadness, longing, anxiety. Let's see how the sodium salt will cope with a brass cartridge. We can try to return the appearance of the coin in the good old way. We polish the coin with an iron brush to make it shine. We will make an articular patina by using a 33% sulfuric ointment, purchased at a pharmacy. In the first seconds after rubbing it in the coin, you can see how it darkens. Copper reacts. The next day, we rub the coin with a soft cloth until relief, and all letters appear. In any case, now this coin is much more readable than it was before, but these shells on the relief. In short, never do that. In the next experiment, we sprinkle a little soap in the gastronomic container and pour a little water. Such an alkaline solution cleans silver and gold from any adhering organic dirt. This is especially true if the jewelry has a complex shape. The bath is easy to handle with the hard-to-reach spots. If instead of soap you pour alcohol gasoline solution into the container, then you clean the printed circuit boards from rosin. Using white spirit, you can clean Ivazovsky's brushes. Also, with the help of the bath, you can quickly etch printed circuit boards. Printer repair companies use this method to clean clogged snouts and nozzles in cartridges with a special flushing fluid. Time to take stock. Someone will surely wonder why should I do such nonsense if I can buy a similar bath at AliExpress for only 30 bucks. In cheap bath there are small piezoelectric radiators, and there is simply not enough power to develop cavitation. Now a few facts about the film. The entire process of creating the ESU took about 3 months. The shooting itself took 1 month. The rest of the time spent to edit it, write and translate text and voice acting and so on. Now perhaps I'll go and cool my tongue, which is smoking from overheating in the remnants of the cold beer that is waiting in the refrigerator. As Japanese wisdom says, no one stumbles while lying in bed. That's all. It was hamster time. Don't subscribe to the channel. Put dislikes and all that. Likes and all that. Likes and all that.